Now let's see the overview of compiler phases. So what are the compiler phases? You have already seen that these are the phases of the compiler. Compiler is a big software. This is a very huge software. There are millions of lines of codes are there, okay, or maybe lakhs of lines of codes are there. So you can see this compiler, what it will do, it will do the compile, okay, so it will do the compilation. This compilation process, this compilation process, basically you can divide into a sequence of phases. Okay, this complete process, this compilation process, you can divide into a sequence of phases. Okay, means first lexical analysis will happen, then syntax analysis will happen, then semantic analysis will happen, then intermediate code will be generated. Okay, then intermediate code will be optimized, then machine code will be generated, and then machine code will be optimized. Okay, so this is the, I can say, sequence of compilation process. This is the sequence. Now we will discuss all these stages, or I can say all these phases, we will discuss in detail in this lecture. We will see a detailed overview of all the phases in this lecture. Now let's see the overview of compiler phases with one example. Okay, I will take one example and we will see the detailed overview of all the phases. Let's see the detailed overview of all the compiler phases. So these are the compiler phases. Let's see the overview one by one, what they will do. Your input is the source code, your source program, that is the input. Okay, so first what will happen? First the lexical analysis will happen, yes or no? So you can see the first step in the compilation process, the compiler will do the compilation. In the compilation process, the first step is a lexical analysis. Okay, what this lexical analyzer will do? Lexical analyzer will read your source code. Your source code, your lexical analyzer will read from left to right, from top to down. Okay, and what it will do, let me tell you. So you can see lexical analysis, this is the first step, this is the first phase of the compilation process. You can also call it scanning. Now what it will do, you can see here that your source code, that is the character stream. See, your source code, that is a sequence of characters, that is your source code. You can say that is the sequence of characters. Now what this lexical analyzer will do, it will read your source code from left to right. You can see, so the lexical analyzer will read the source code from left to right, and it will convert your source code into token stream, into stream of tokens. Okay, so very simple. You can see the stream of characters means that is your source code. Your source code will be converted. First you will read the source code, the lexical analyzer will read the source code from left to right, and it will generate tokens. It will generate tokens. Now what is a token? This word token, what is a token? Token is a logical unit. Token is a token. What was it? What is a token? Token is basically logical unit of source code. Unit of source code. Logical piece of source code. I can say this is a logical piece of source code. So what is a token? Token is a logical piece of source code. Don't worry, it will become clear. Now you can easily see that tokens, basically, tokens have a collective meaning. I told you, because token, basically, that is a logical piece of the source code. Examples of tokens are like identifiers. Okay, identifier, this token you will give for user defined names. Okay, if you have a user defined variable, then for user defined words, for user defined names, you will give this token identifier. Okay, you can give this some, I can say, for reserved words, for keywords, you can give another token. Okay, for integers you can give another token, for doubles floats you can give another token. Okay, for operators, for delimiters, for special symbols, you can give another token. Okay, so let's understand actually what it means, what is happening here. Let me give you one analogy. Okay, let's understand what this lexical analysis means. Is this clear? What this lexical analyzer will do, let's understand this very clearly. So let me give you one analogy. Let's assume you go to a cafe. In that cafe, let's assume you order masala tea, ginger tea, filter coffee, cold coffee, and pav bhaji. Okay. Now let's assume that pav bhaji has no variations. See, there are variations for tea, masala tea, ginger tea. These are the variations of tea. Okay, there are variations of coffee also, cappuccino, filter coffee, cold coffee. These are the variations of coffee also. Let's assume that pav bhaji has no variation. Let's assume this pav bhaji, this is unique. Okay, there is no variation. Now in this situation, you tell me one thing. In this cafe, on the counter, you will go to the counter. Okay, so on the counter, will they generate coupon for masala tea, ginger tea, like that? Will they generate coupon for every separate thing? No. See what they can do. They can generate coupon for tea. They can generate coupon for coffee. Let's assume in this cafe, they have coupon for tea. They have coupon for coffee. They don't have coupon for masala tea. They don't have coupon for ginger tea. They don't have coupon for filter coffee, and they don't have coupon for cold coffee. Let's assume they have coupon for pav bhaji also. So are you getting my point? Now what they will do? Now they will generate coupon, but the coupon are only two, either coffee or tea. There are only two tokens. These are the tokens. Okay. Now what will happen? Let me tell you. So you can see what will happen. What this cafe will do. So for this masala tea, what this cafe will do? For this masala tea, the cafe will create a token. For this masala tea, the cafe will create a token. It will generate a token, and the token will be like this. The token will have two things. The token will have two things. One is token name. The token name is T. Yes or no? The token name is T. So one is token name, that is T. Token name is T. TEA. Okay. So this is the token name. And the token value. What the token value? See, the token name is T, but the token value is masala tea. Is this clear? Masala. So something like this. Is this understood? So this complete thing is your token. This complete thing is called token. So remember, this complete thing, if you look at this complete thing, this is called token. This complete thing is your token. This is the token that will be generated when you order masala tea. Then this token will be generated. Here, this is the token name. Here, this is the token name that you are ordering tea. And this is the token attribute. Or I can say this is the token value. You can say this is the token attribute. Your token is T. And for that T, what the attribute? So you can say it is token attribute or token value. Did you understand this? Please tell me. Did you understand this analogy? Did you understand? Let me know. Okay, similarly for ginger tea, what will happen? For ginger tea, another token will be generated. Another token will be generated. The token will be like this. The token name is tea. Okay, but the attribute is ginger, or I can say the value is ginger. This is additional information. This is attribute for this token. Okay, the token name, that is T, and this attribute, or I can say this is the value of the token, or I can say this is the additional information about the token. Is this clear? This is the additional information about the token. Is this clear? Please tell me. Similarly for filter coffee, similarly will happen for filter coffee. For filter coffee, a token will be generated. A token will be generated. The token will be coffee. The token name will be coffee, but there will be additional information. That additional information is basically the attribute of this token. Okay, what are the attribute of this token, or you can say value of this token? That is basically filter. Is this clear? I hope this point is clear. Similarly for the cold coffee, the token will be generated, that is coffee. This is the token generated, and the attribute of this token, the value of this token, or I can say the additional information about this token, that is called. Okay, and finally this pav bhaji. For this pav bhaji, let's assume there is a token that is pav. That is very simple. The name of this token is TPAVBH. Okay, is this clear? So let's assume this is the name of the token. And now there is no attribute, right? There is no attribute. There is no attribute required. Is this clear? There is no attribute required. So you can see, this is the idea. I hope you understood this idea. So can you notice, this is what I'm telling you, what this lexical analyzer will do? It will read your program. This is your source code. Okay, what your lexical analyzer will do? It will read your source code from left to right. Okay, it will read from left to right. And what it will do? It will generate tokens. Now, did you understand that token is a logical unit? Token is a logical piece of source code. Piece of source code. Okay, so basically your source code, from that source code, this lexical analyzer will generate a token stream, a stream of tokens. Now here you can easily see, for example, if you have user defined keywords, then this token you can generate, the identifier token you can generate, the name of the token can be identifier. Okay, yes or no? If you have user defined variables, like you are defining some variable I, variable j, so for these variables, what you can do, so you can see, you can generate token with this name, token with name identifier. Okay, for keywords, for the reserved words, you can generate identifier with the same name. Like for integer, okay, for while, there is while. So while is a keyword in the C language. For while, what you can do, you can generate a token with while name. The name of the token is also while. Is this clear? The name of the token is also while. So very simple. Similarly, for integers, you can generate tokens. Okay, so for everything, basically for everything, you will generate tokens. I hope you understood. Let's see this example. Consider this program. Now, when this program will go through the lexical analysis, then what will happen? This program is there. Now, the lexical analyzer, what it will do? It will read this program from left to right. The lexical analyzer will read this program from left to right. Okay. Now you are reading this program from left to right. So first I will come. Is this logical unit? Tell me, will you ever read this as this is a logical unit? Is this logical unit of the source code? Do you think this is a logical unit? Is this some I can say, does it have some separate existence? I want to ask, this does it have some separate existence, some separate value? Is this a logical unit? No, this is not a logical unit. Yes or no? This is also not a logical unit. Yes, this is a logical unit, right? For example, in the analogy, the masala tea. Okay, you can see this is not a logical unit, right? But this complete thing is a logical unit from the cafe point of view. I can say this complete thing is logical piece. Okay, yes or no? Logical piece or logical unit. But you can see this is not logical unit. This is not a logical unit. Agree? So from the cafe point of view, so very simple. So this is the same idea here. You can see this is a logical unit. This is a logical unit. So for this int, what, because this is a keyword. Is this a keyword in the C language? Yes, this is a keyword. So for this int, what you can generate? This token you can generate t int. Okay, token int means the name of the token is int. Okay, this token you can generate and you don't need any value. Yes or no? You don't need any value. So this is the token you can generate. This is the token you can generate, and there is no need of any attribute because this is the keyword. Is this clear? Now, this white space will be ignored. Okay, there is a white space here. Yes or no? There is a space here. That space you can ignore. In the C language, the space basically that you can ignore. Okay, so basically this lexical analysis will ignore the space. Means for this space, you will not generate any token. Please understand. For this space, the lexical analyzer will not generate any token. The lexical analyzer will ignore this space. Will ignore this space. Then for this A, is this a logical unit or is this a logical unit? Tell me. Is this complete thing as a logical unit or is this a separate logical unit? This is a separate logical unit. Yes or no? So you can see for this A, this is a logical unit. Because this is a user defined keyword. This is a user defined variable. This is not a keyword in the C program. In the C language, this is not a keyword. This is user defined variable name. So for this, what you can do, you can generate the token with this identifier. The token name can be identifier. And what the value? What is the value of this token? What is the value of this token? That is A. The value of this token is A. This complete thing is your token. This complete thing is your token. Is this clear? Here, this is the token value. You can say this is the token attribute. Or you can say this is the token value. Or you can say this is the token value. Okay. And what is this? This is token name. This is token name, right? Is this clear? This is token name. I hope you understood. Okay. So very simple. Now, one more thing, that this is a special symbol. For this special symbol, what will happen? Again, you will generate a token. This is a special symbol. You can generate a token with this name, like a special symbol. Okay, you can generate token. The name of the token can be this. And for the token value, the token value is this. Okay, the token value is this. Is this clear? Then finally, this new line is there. Do you understand? There is a new line here. After this line, there is a new line here. Okay, this new line is also ignored by the lexical analyzer. The lexical analyzer will not generate any token for the new line. For the new line, you can see you are going to the new line. Yes or no? You are going to the new line. So for this new line, the lexical analyzer will not generate any token. Then again, one token will be generated for this, one token generated for this, one token generated for this, for this, for this, for this. So like this, tokens are generated. Is this clear? Please tell me. Okay. Let me tell you one more thing. The exact details, they will depend on the compiler. Yes or no? The exact details, like what are the token names, what token names you can use. Okay. So everything basically, that the exact detail will depend on the compiler and also the source language. So this is just an overall idea. What I told you, this is just the overall idea, remember. So the exact details, like what are the token names, how many tokens are there, how many categories are there. Okay. So the exact details will depend on the language, on the source language, also on the compiler. For example, what a compiler can do, what some compiler can do. Some compiler, what it can do, instead of putting this value here, you can put this value in the symbol table. In the symbol table, you can put this value, and that index you can put here. Is this clear? Is this point clear? See, some compiler, what some compiler can do? Some compiler can do like this. Like for example, let me take this one A. For this A, some compiler, what it can do? It can store in the symbol table. This is your symbol table. In the symbol table, you can store this A. The lexical analyzer, what it will do? In the symbol table, let's assume at this address 1. At this address 1, you are storing this A. Okay. And that this is identifier. This is identifier, right? This is identifier. Okay. So you are storing this here, that identifier, and the value is A. So what you can do? You can simply do this, that this is the token name is identifier, or I can say token name can be ID. Token name can be ID. And instead of putting this value here, you can put this index, the symbol table index. This is your symbol table. The symbol table index you can put. Anyway, what I want to tell you, the exact details will depend on the compiler and also the source language. Okay. So you can see, if you study the Ullman book, then you will find this type of explanation for the lexical analysis. You will find this type of explanation if you study the Ullman book. Then you will find that in the token, this is the token, remember, this is the token, this is the token. But instead of putting the attribute value, this attribute value, instead of putting that attribute value, you can put the symbol table index. In the symbol table, you can put it. You can store this value A, you can store in the symbol table, and this index you can put in the token. Okay. So anyway, either you can do this, or this explanation is from the Stanford. Okay. This is the explanation from the Stanford. You can easily see. Okay. But anyway, don't worry about it. You just understand what token means. Okay. What is happening here? You just understand that. Is this clear? Please tell me. So you can see, if you have this program, then for this program, you can see these are the tokens that will be generated. Okay. These are the tokens that are generated. Is this clear? Now, one more thing I want to tell you, like for example, if you write this, okay, if you write this int, and let's assume some name you are writing. Okay. So let's assume some ABC, int ABC. Now, let me tell you one thing. See, this is the source code, right? Yes or no? This is the source code. Okay. This is the source code. Now, for this ABC, a token will be generated. For this ABC, a token will be generated for this ABC. What is the token that generated? Tell me, what is the token that will be generated? The token will be generated is this, that this is identifier, because this is user defined key, user defined variable name. Yes or no? This is user defined variable name. So you can give this token identifier. This token you can give. Okay. That token name will be identifier. Okay. Token name will be identifier, and the value of this token, or I can say the attribute of this token, that will be ABC. This is the additional information about the token. Okay. The value of the token is ABC. So you can see, this is the token name. This is the token name. This is a token attribute. Token attribute. Okay. And let me tell you one more thing. This ABC, which is part of source code, this ABC is called lexeme. This is called lexeme. Is this clear? This ABC is called lexeme. So what is a lexeme? Lexeme is basically the part of source code for which you have generated the token. For this, you have generated the token. So this is called lexeme. What is lexeme? This is a piece of source code. This is piece of source code for which token generated. for which you have generated the token. For which token is generated. Okay, understood? Is this clear? Let me know. For example, if you have this while, okay, let's assume something. Now you can see this is your source code. This is your source code, right? Now, in this source code, for this, a token will be generated. Agree? Okay, a token will be generated. For this, this is a keyword in the C language. This is a keyword. So the token name you can give. This is the token name you can give. T while. Okay, T while. This is the token name you can give. So you can see this T while. This is the token name. Please understand. T while, that is the token name. And there is no attribute. Okay, there is no attribute. You don't need any attribute. Now, the part of source code for which you have generated the token, that is called lexeme. This is called lexeme. Is this clear? So what is a lexeme? Lexeme is part of the source code for which you have generated the token. This is the token that you have generated for this part of the source code. So remember, this is the part of source code. Please understand. This is part of source code for which token is generated. Token is generated. Understood? Is this clear? Okay. So here you can easily see a token will be generated because this is a keyword. This is already a keyword. So this is your lexeme. Can I say these are the lexeme? Is this clear? These are the lexemes. These are lexemes. Okay, what are these? So let me write it here. These are lexemes. So very simple. Now you can see this is the token name. Okay, so like that. Okay, you can easily see. Like this is identified. This is the token name with the value A. With the value A. Okay, so like that you can easily see. Anyway, so let's move on now. So you can see this is lexeme. This is the piece of original program. Please understand what is a lexeme. What is the definition of lexeme? That is the piece of original program from which you have generated the token. Okay, and this is the token name. And this is the token name. Similarly, you can see this is the attribute. This 137, this is the token attribute. Okay, so you can easily see all these things. Now you can see the lexical analyzer. It will produce the token of the form token name attribute value. Okay, this is how the token will look like. This is how the token will look like. Token name and attribute value. Okay, let's move on. Like you can see for this is the token. For this is the token. Okay, for this is the token name. This is the attribute value. Right. Okay, for this is the token name. This is the attribute value. So like that. Anyway, you can easily see all these examples you can see. And remember, white space, new line, tab, all these things are ignored. Okay, for this white space, there is a space here. There is a space here. There is a new line. There is a tab. Okay, so for all these things, you have new line, you have white space, or you have tab. Okay, for all these things, remember, for all these things, the token will not be generated. For all these things, token will not be generated. We will not generate the token. Okay, we will ignore all these. So these will be ignored by the lexical analyzer. The token will not be generated. Okay, I hope everything is clear. So you can see in this example also, you can notice if this, for this, a token will be generated. Okay, because this is a keyword. If is a keyword, so the token name can be if. Okay, similarly, for this left parenthesis, this token will be generated. Left parenthesis. For this identifier token will be generated and the value will be X. For this greater than equal to token will be generated. Okay, for this greater than equal to token will be generated. Okay, is this clear? So very simple. Remember what tokens will be generated, what are the names of the token, how many token categories are there. Everything will depend on the compiler and the source language. So please understand. You might be thinking, sir, like let me give you one example so that you can clearly understand. For example, consider this like less than equal to. Okay, less than equal to. Now, one compiler, what it can do for this compiler number one, what it can do? Compiler number one can generate token maybe it can generate token with this name, that less than equal to, less than equal to. Okay, the token name can be less than equal to. Is this clear? The token name is less than equal to. There is no attribute value. There is no attribute value. But for this, compiler 2, what it can do? Compiler 2, what it can do? It can generate token like this. It can generate token like this, that this is an operator. This is an operator, and the value, the attribute is this. Okay, I hope you understood. Is this clear? So everything will depend on the compiler. Is this clear? What is the token name? How to generate the token? How many categories are there for the token? Everything that will depend on the compiler. The exact details will depend on the compiler. Please understand. Okay, is this clear? Let me know. Is this point clear? Okay, so you can see if this is your program, if this is your source code, then these are the tokens that can be generated. And you can easily see this is the attribute. This is the token attribute. Okay, so like that, these are the token attributes. So very simple. Now let's move on. The next phase of the compiler, that is syntax analysis, or you can say that is parsing. In this syntax analysis phase, what you do? You will check for the syntax, right? Yes or no? So very simple. In this syntax analysis phase, what you will do? The input is the token stream. The token stream that you got from the lexical analyzer, that token stream is the input for the syntax analyzer. What the syntax analyzer will do? It will check for the syntax. It will check for the syntax. Is the program, your source program, does it have correct syntax? Okay. And remember, to check for the syntax, whose help it will take? Tell me. The syntax analyzer will check for the syntax using context-free grammar. Yes or no? Using context-free grammar, right? Because whatever is your source language, for that source language, there is a context-free grammar. Now, with the help of that context-free grammar, this syntax analyzer will check for the syntax. So remember this syntax analyzer, or you can say this is parser. What it will do? It will verify, is your syntax correct? If the syntax is not correct, then it will give you syntax error. Okay, if the syntax is not correct, it will give you syntax error. And the output of this syntax analyzer, that is syntax tree, or you can say parse tree. Okay, or you can say parse tree. The output of this syntax analyzer, that will be syntax tree, or you can say parse tree. Very simple. So you can easily see, if this is your code, then syntax analyzer will check for the syntax. Okay, is the syntax correct? With the help of context-free grammar, remember, this syntax analyzer, it will check for the syntax using context-free grammar. And if there is any mistake, if there is any syntax mistake, then it will give you syntax error. Okay, otherwise the output of this syntax analyzer, that will be a parse tree, or I can say syntax tree. Okay, now let's see the next phase, that is semantic analysis. What this semantic analysis will do? The name itself is telling you semantic means meaning. Yes or no? This name itself is telling you semantic means meaning. Meaning of the program must be correct. Means, does your program make sense? See, syntax may be correct, but does your program make sense? Okay, means all the instructions in the program, do they make sense? So this is what a semantic analysis will check. So remember what the semantic analysis will do? Semantic analysis, it will ensure that program has well-defined meaning. Means all the instructions in the program, they make sense. Okay, is this clear? For example, you tell me one thing. If you are using some variable without declaring, can you use it? Tell me. Means undeclared variable. You did not declare the variable. Can you use it? No, you should not use. Yes or no? So you can see this is semantic analysis. This is part of semantic analysis, that variables which are not declared, they should not be used. Or I can say variables which you are using, they must be declared before they are used. So you can see this is checked by the semantic analysis. Is this clear? So very simple. Remember semantic analysis, this will make sure, this will check whether your instructions make sense. Okay, this basically checks for sensibility of the instructions. You can say for sensibility of instructions. Means, do they make sense? For example, you can easily see what the semantic analysis will do. In this phase, you will check that variables must be declared before they are used. Also, if you are writing some expression, okay, if you are writing some arithmetic expression, then the types must match. Okay, type mismatch must not happen. Let me give you one example. See, what is the type error? When the type error will come? Type error will come when you are performing operation on the values which do not support that operation. Okay, for example, this kind of type error. See, what is a type error? Let me tell you. This type error, type mismatch. You can say type mismatch error. Type mismatch error. Now, what is that? Type mismatch error. So, for example, let's assume you have some string. Okay, some string you are multiplying with integer. So then type mismatch will happen or not? Yes or no? You have some string. This is a string, and you are multiplying this with some integer. This is integer. Now you can easily see that this string cannot support. Very simple point. This is what I'm telling you. Read this. The type error will happen. The type error will arise when the operations are performed on values which do not support that operations. Like this string, this does not support multiplication. String does not support multiplication. So you can see that here the type mismatch will happen. Is this clear? So you can see type mismatch will happen when the operation, multiplication operation is performed on the values which do not support this operation. Okay, so this is a very simple idea. This is the idea of type mismatch. So you can see this semantic analysis phase. In this phase, we check for type mismatch. Okay, so remember type checking. Type checking is done in this phase. Also, scope checking is done in this phase. Okay, also scope checking. So basically, many things are done in this phase. Scope checking, type checking, okay, checking whether variables are declared before they are used. So basically, many things they are checked, they are verified in this phase. Okay, is this clear? In this phase, these are the things that we do. Let me tell you one more thing. The major task of semantic analysis is type checking. This type checking is the major task of semantic analysis. If someone asks you, like, what are the major task? The major task of semantic analysis, what is that? The major task of semantic analysis. Semantic analysis will do a lot of things. Okay, it will do a lot of things, but the major task of semantic analysis is basically type checking. Okay, that is a major task. Anyway, so tell me one thing. If you have this program, is there any type mismatch here? In this program, do we have any type mismatch? Look at this program and tell me, do you have any type mismatch here? We have a array, integer array you have. Okay, in this first line, there is no problem. In this first line, there is no problem. This C is an integer variable, and this ARR, this is an array of size 2. Okay, so there is no problem in this line, right? Okay, in the first line, there is no problem, right? Agree? Syntax is correct. Actually, if you notice, there is no syntax error. There is no problem with the syntax. Syntax is correct. Okay, the syntax correct. There is no syntax error here. Yes or no? Everything is correct. You can say syntax is absolutely correct. Okay, so you tell me, is there any type mismatch? Yes, of course. See, this is the array name. You are multiplying with 10. So here there is a type mismatch because you cannot multiply this array name. You cannot multiply with some integer. Yes or no? So you are performing this operation on values which do not which do not support this operation. Did you understand? You are performing this operation on values which do not support this operation, so here there is a type mismatch. Is this clear? Please tell me, let me know. So here you can notice there is a type mismatch. Okay, so this analysis is done in the semantic analysis phase. Okay, so you can see the semantic analyzer, it will do many things, remember. Okay, type matching, type checking is one of them. The semantic analysis will do a lot of things, like it will check for undeclared variables. If you are using some variable, it must be declared before you are using it. Okay, and scope checking, type checking, all these things, they are done by the semantic analysis phase. But type checking is major, I can say. The most important task of the semantic analysis, that is the type checking. Okay, so you can see what this semantic analysis can do for type checking. If you want to check the type, then what you can do, you can basically the syntax tree that you are getting, this syntax analyzer will give you the syntax tree. In that syntax tree, you can annotate that syntax tree and you can check for type. Okay, so basically this syntax analyzer will give you syntax tree. What the semantic analysis will do for type checking, this will annotate this syntax tree. So basically you will get the output of this semantic analysis, that is annotated syntax tree. Is this clear? The output of semantic analysis, that will be annotated syntax tree. Okay, so this is the idea. Okay, let's move on now. The next phase of compiler, that is intermediate code generation. Now this is interesting. So far you already know what is lexical analysis, what is syntax analysis, semantic analysis. So let's see what is this intermediate code generation. In this phase, we will generate the intermediate code. Is this clear? In this phase, we are going to generate the intermediate code. I told you that intermediate code is machine independent and source language independent. So in this phase, what we are going to do, we are finally going to generate the intermediate code from the source language. Okay, you have a source program. That source program will be converted into the intermediate code. Okay, so you can see here, you have a source language, the front end, the last stage of the front end. If you notice, the last stage in the front end, that is intermediate code generation. Okay, what this intermediate code generation will do, it will generate the intermediate code. Okay, so let's see. Now let me tell you one thing. We will study in detail, don't worry, in future we will study. But this intermediate code, intermediate representation, there are many types of intermediate representations. The intermediate representation, actually there are many types of intermediate representations. Many are there. Okay, so intermediate representation, I can say there are many types. Many types of intermediate representations are there. Many types of intermediate representations are there. We will study all of them in detail, don't worry. Okay, like for example, let me tell you some examples. Let me tell you, like very popular, that is 3 address code. There is very popular intermediate representation. This is very popular, that is 3 address code. In short, we call it TAC. This is very popular. Another intermediate representation is SSA, single static assignment. Don't worry, we will study this also in detailed way. Another intermediate representation is control flow graph. Control flow graph. Okay. Another intermediate representation is syntax tree. Your syntax tree. Okay, syntax tree. And there are many more. Okay, and there are many more. Don't worry, all of them we will study. So you can see that intermediate representation, there are many type of intermediate representations are there. Now, you can use 3 address code for intermediate representation. You can use SSA, single static assignment, for intermediate representation. You can use control flow graph. And remember one more thing, you can use multiple. It's not that you have to use only one of them. No. Okay, you can have, during the compilation, multiple intermediate representations can be generated. Is this clear? During the compilation, when you do the compile, then during the compilation, multiple intermediate representations can be generated. Okay. Anyway, today all these we will study in detail. Don't worry. The 3 address code, SSA, control flow graph, syntax tree, DAG, okay, postfix, all these intermediate representations we will study in detailed way. But in this lecture, let me just take example of 3 address code. Okay, because this is very popular. So let me take example of 3 address code. Now, this is your source code. This is your source code. Okay, now let's convert this to intermediate code. Okay, what we are going to do, we are going to convert this to intermediate code. The intermediate code. Okay, and I'm assuming that for intermediate code you are using 3 address code. Okay, I'm assuming, as I told you, there are many different intermediate representations. There are many different intermediate representations are there, but most popular is 3 address code. Is this clear? The most popular intermediate representation, that is 3 address code and control flow graph. These are the most popular. Okay, so 3 address code. Okay, anyway, so let's see. The name itself is telling you 3 address code. What that means? Let me just tell you a quick idea. In the 3 address code, instructions are very simple and they will use at most 3 addresses. Okay, simple instructions using at most 3 addresses. Simple instructions using at most 3 operands. Using at most 3 operands. Is this clear? Using at most 3 operands. So remember, in the 3 address code, the instructions are very simple and they will use at most 3 operands they will use. For example, how many operands are here? Tell me. In this source code, how many operands are there? In this, how many operands are there? Total, how many operands? Total 5 operands are there. Okay, so in the 3 address code, how you will convert this source code, how will you convert this to 3 address code? Very simple. Okay, first you will do this B into C. Okay, no problem. Do the B into C and you store this in some temporary variable T1. Okay, you store this in some temporary register T1. This T1, this is a temporary register, or you can say this is a temporary variable. Okay, you can say this is a temporary variable or temporary register. So what you do B into C, you store that into T1. Okay, because remember, in the 3 address code, we have instructions are very simple and they will use at most 3 operands. Yes or no? At most 3 operands you can use. This instruction will use at most 3 operands. Okay, every instruction will use at most 3 operands. So this is the idea of 3 address code. 3 address code is an intermediate representation. There are many different type of intermediate representations are there, but the most popular intermediate representation, the most popular type of intermediate code, that is 3 address code. Okay, in this 3 address code, the instructions are very simple and they will use at most 3 operands. So if this is your source code, you can convert this into the 3 address code very easily. What you do B into C and you store this in a temporary variable T1. Then what you do? Then you do B into D, you store that into temporary variable T2. Then what you do? Then you do T1 plus T2. Yes or no? Then you do T1 plus T2. See, B into C, this you are putting in the T1 and this you are putting in the T2. Then you will do, then what you will do? Then you will do T1 plus T2. Okay, what you can do? You can store this in T3 or maybe you can directly store in A. Either you can do this, either you do this, or what you can do, you can store this in T3 and then this T3 you can store in A. Okay, so this is the complete idea. Is this clear? This is your intermediate code. Please tell me, did you understand? Let me know. Very simple. See, this is nothing hard here. Very simple. This is your intermediate code in 3 address code. So this is the 3 address intermediate code. 3 address intermediate code. Okay, let's move on. So you can easily see this is what you will get. Okay, let's see this one. How to convert this into 3 address code? Give me 3 address intermediate code, or I can say intermediate representation. What that will be? So very simple. Here what you will do? This is a while loop. So there will be a loop here, right? Yes or no? There will be a loop. Now let me try. Because you want 3 address intermediate code. Yes or no? What you want? You want 3 address intermediate code. 3 address intermediate code you want. So what you will do? Anyone? Just tell me, if you have this code, first what you will do? In this code, first, what is the first thing you will do? Just tell me that point. Okay, when you are executing this, what the first thing you will do? Just tell me that. First thing, what you will do? You will do y plus z. Yes, very good, very good. First thing you will do is y plus z. Okay, let's put this y plus z in some variable T1. Okay, this y plus z you will do. Let me put it in a T1. Okay, I'm putting this in T1. Then what you will do? What is the next thing you will do? Tell me. What is the next thing you will do? You will compare this x. You will compare this x with T1. Yes or no? Okay, let me put that in T2. So did you notice this T2? This is a Boolean. Yes or no? Either T2 will be 0 or 1. Do you agree with me? Okay, see, notice. First you will do y plus z. Put this in temporary variable. This is a temporary variable T1. Put here T1. Now, then what to do? Then you check x is less than T1 or not. You check x is less than T1 or not. And the result you store in T2. Did you notice one thing, that this T2 will be what? Can I say this T2 is Boolean? Either this T2 will be 0 or 1. Yes or no? This T2 will be a Boolean variable. This is a temporary variable, but this is a Boolean temporary variable. Okay, either it will be 0 or 1. If x is less than t1, then it will be 1. If else it will be 0. Yes or no? Is this clear? Please tell me. See, a very simple point I'm telling you. If you write like this, in the t2, you are putting x less than t1. Now, what will happen here? It will happen that if x is actually less than t1, then this will be true. Yes or no? If x is actually less than t1, then this will be true. Then in this situation, t2 will be true. T2 will be true. Okay. Else, if x is greater than equal to t1, then in this situation, t2 will be false. Right? Yes or no? Okay. Very simple. Is this clear? So quite easily you can do. I hope this point is clear. True, or you can say 1, and false, or you can say 0. Either you can say true or you can say 0. False means 0. True means 1. So very simple. Now here, this is what you will do. What is the next thing you will do? Tell me. When you are executing this code, what is the next thing you will do? The next thing you will do, if this T2 is set, then you will go here. Do you agree with me? Do you agree with me that if this T2 is true, then you will go to this line? Yes or no? Is this clear? Please tell me. So what you will do, this is what you are going to do. If this T2, if this T2 is true, then what you will do? Or maybe you can do like this. If T2 is false, then go out of the loop. Agree with me? If T2 is false, okay, if false T2, if Z, T2, okay, I will explain, don't worry. So let's write the if IFZ. What this IFZ means, what I will tell you. IFZ T2. If this T2 is false, then what should we do? Please tell me. Then we should go to where? We should go out of the loop. Yes or no? We should go out of the loop. Agree with me? We should go out of the loop. Do you agree? Please tell me. Did you understand what I'm telling you? If this T2 is false, if this T2 is 0, this means if T2 is 0, then you go out of the loop. Okay, so I'm telling you what this means, what this line means. When I say if Z A, if Z A, or maybe if Z T go to L1. Okay, what that means, let me tell you. This simply means if T2 is 0, or you can say false. If T2 is false, then jump to L. Okay, then jump to L. Is this clear? So this is what we are going to write, that if this T2 is 0, okay, if Z T2 means if this T2 is 0, then go out of the loop. Okay. If this is not satisfied, then what to do? If this is not satisfied, means if this T2 is true, then what to do? Tell me, then what to do? Then in X, you put X minus 1, X minus Y. Okay, yes or no? Is this clear? Please tell me. L1 is here. Okay, after this instruction, where you will go? Tell me. Just tell me, after this instruction, where you will go? Just let me know after this instruction where you will go. See, this is very common sense. Okay, everything is very simple. First, what you will do? First, you will do y plus z. Do this y plus z and put in t1. Store in temporary variable t1. Then you will check x is less than t1 or not. X is less than t1 or not. Store the result in t2. You can see t2 is Boolean variable. If x is less than t1, if this is true, then this will be true. If this is false, then this will be false. Okay. Now you can see if this T2, if this is false, then you will go out of the loop. Okay. Means you will go to L1. If this T2 is false, you will go out of the loop. You will go out of the loop. Okay. Else, if this T2 is not false, okay, if this T2 is true, then you will execute x equal to x minus y. After this line, you will go again to y plus z. Yes or no? After this line, you will again go to y plus z. Again, you will do y plus z. After this line, you will again do y plus z. Yes or no? Okay. After this line, what you will do? You will go to L. You will go to L0. Okay. You can go to L0. This is your L0. Okay, this is your L0. So that's it. This is your program. Please tell me, did you understand? Did you clearly understand how to convert, how to write intermediate code? This is the intermediate code we will get. Did you understand this one? Please tell me. This one, did you understand? Let me know. This is your program. This is the source code. And we are converting this source code into intermediate code. 3 address intermediate representation. Did you understand? Let me know. Please tell me. Now, Satyam is asking, why can we not go to second instruction? See, that is a good doubt. I will explain that. But notice one thing. Here we are not doing any optimization. Satyam, we are not doing any optimization here. Okay, just focus on this code, what this code is doing. After this line, again, you will do this y plus z. Yes or no? Do you agree with me? Forget about optimization. Forget about optimization. After this code, again, you will go here. Yes or no? After this code, again, you will do this y plus z. Is this clear? I will answer your doubt. What you are thinking, I understand that. Okay, so that will come. That will come. But did you understand this? That after this line, you will again do y plus z. Then again you will do comparison, and then again the same thing will happen. Okay, so this is the idea. Understood? Okay, this particular example, did you understand? So you can see this line. What this line means? If zt1 go to L1, what this means? This means go to L1 if t1 is 0. Go to L1 if t1 is 0. And what this means? This means go to L1 directly. Okay, directly jump to L1. Directly jump to L1. Okay, and this L1 is some label here. So very simple. Okay, so you can see if this is your code, source code, you can convert into intermediate code. So finally, this is your 3 address intermediate representation. 3 address intermediate representation. This is the intermediate representation. Okay, is this clear? Now, did you notice one thing? Is this machine dependent? Did we use any feature of the machine? Please tell me, when you are writing this code, did you think about the machine, the target architecture, the target machine? When we are converting this to this, did you think about the machine, the target machine? Did you think about? No, you did not think. Yes or no? So this is basically machine independent. Yes or no? Target machine independent. This is target machine independent. Okay. Also, this is a source code independent. This does not depend on the source language. Like, does this depend on the C language? Is there anything related to C language here? Is there anything related to Java language here? No. So you can see this is a target machine independent. Also, this is a source language independent. This is source language independent. Okay. Now let's move on. Now the next phase, what is that? The next phase is intermediate representation optimization. This intermediate representation that you have, can you optimize it? Optimization means making it better. Yes or no? What optimization means? That simply means making it better. What the meaning of optimization? Code optimization. What the meaning of code optimization? You are making it better. You are making it faster. A code optimization means doing some changes such that code becomes faster. Okay. So remember, code. This means doing some changes. Doing some changes. We will do some changes in the code to make it faster. To make it faster and shorter, smaller. Okay, so this is what optimization means. You make it faster, you make it more efficient. Okay, execution time should be less. So basically, you are making the code better. Now, let me ask you a very simple point. This is the code we have already seen, right? Yes or no? Okay, this was your intermediate code that we got. Agree? This is the intermediate code that we got, right? This was the intermediate code that we got. Can you optimize it? This is the intermediate code that we got. Can you optimize it? Let me know. Can you optimize this? Now we are learning intermediate representation optimization. Remember, IR optimization. IR optimization. We are going to optimize the intermediate representation. The intermediate code we are going to optimize. So this is machine independent. Yes or no? This optimizer is machine independent because this is optimizing the intermediate code. Intermediate code is machine independent. So this optimization is also machine independent. Okay. So tell me, quickly tell me, can you optimize this? This intermediate code that we got, this intermediate code, can you optimize? Can you optimize? Can we optimize? Can we make it better? See, in this intermediate code, notice one thing. Again and again, you are doing y plus z. Just notice one thing. Are you doing this y plus z again and again? Yes or no? This y plus z, in every loop, you are doing y plus z. Is that stupidity or not? In every loop, if this loop runs, let's assume 1,000 times, how many times this addition you will do? Let's assume this loop, if this loop, let's assume this runs 1,000 times. Okay, if this loop, if it runs for 1,000 times, then how many times this addition will happen? Then 1,000 times addition will happen, right? 1,000 times y plus z addition will happen. Okay, yes or no? That is stupidity, because are you changing y? This while loop, will it change y? Does it changing? Is it changing y? Is y changing in this while loop? In this loop, y changing or not? Y is not changing. Is z changing? Is z changing? Z is also not changing. Okay, are you getting my point? This is the code while x is less than y plus z. Y plus z. Okay, and you can see that x is equal to x minus y. This is your code. Now you, very simple point you notice, y is not changing, z is not changing in this loop. Okay, no, okay, yes or no? Y comma z are unchanged. They are unchanged by the loop, by the while loop. But still again and again you are adding it. But still, what you are doing? But still, in every iteration you are adding. In every iteration we add y comma z. Yes or no? So this addition is taking a lot of time. Okay, if this while loop, if it runs, let's assume 1 million times, then 1 million unnecessary additions will happen. Yes or no? Still, in every iteration you are adding. This is unnecessary work. Yes or no? This is unnecessary work. This is completely unnecessary work, because neither y is changing nor z is changing. So this addition you don't have to do again and again. What the better thing? Just put it outside. Yes or no? The better thing is put this outside. Okay, so what you can do, this line, this y plus z, you are doing this y plus z. Basically, this y plus z, what you do, you put this outside. Okay, this y plus z, you can store in some variable t0, put it outside the loop, and this t0 you put here. This is the optimized. Yes or no? Can I say this is the optimized version? This is the optimized version. So same thing you can do here. This was your intermediate code. This line, you just keep it out of the loop. Just put it out of the loop, because y is not changing, z is not changing. Yes or no? If y changing, can you put it outside the loop? In the here, if y is changing, then can you put it outside the loop? If y is changing, can you put it outside the loop? No, then you cannot do. Okay, yes or no? If y is changing, then you cannot do. But here, y is not changing, z is not changing, so you don't have to do this y plus z again and again. This you put outside the loop. Here you put this code, you put here outside the loop. So what you can do, this is what you can do. Is this clear? Now you can notice in the loop, you don't have to do any addition. If this loop runs for 1 million times, then you don't have to do 1 million additions. Yes or no? So this is called optimization. This example, did you understand? Did you understand the concept of optimization? What optimization does? What optimization does? You can notice Here you can notice if you are running this loop 1000 times, then 1000 times this addition will happen, unnecessary addition, because y comma z are not changing. So unnecessary addition will happen 1000 times. So what you can do, you can put this line outside the loop. Okay, outside the loop you can put it. Now you can notice that if you run this loop 1000 times, then 1000 time addition will not happen. Only one time addition will happen. You don't have to do addition 1000 times. Okay, so this is your optimization, intermediate code optimization. So this is the simple idea we have already seen. Now the next phase is code generation, or I can say machine code generation, or you can say assembly code generation. What this phase will do, it will generate the assembly code. Very simple. This phase is going to generate the assembly code. This phase is going to generate your machine code or assembly code. I can simply say the target machine code or the target assembly code will be generated. Okay, very simple. Here in this phase, what we will do, the target program will be generated. Very simple. Okay, the target program is going to be generated. Like you can see, if this is your, let's assume this is the output of optimized, let's assume this is the optimized intermediate representation. Okay, this is the optimized intermediate representation. Now this will be the input to the code generation. This will be the input to the code generation phase. And what this code generation phase will give you, it will give you the target machine code. It will give you the target program. Okay, you can say the target code will be generated. It can be assembly code. The target code, I can say the target assembly code. So now assembly code will be generated. Okay, so you can see this program, this is your optimized intermediate representation. Okay, this is the output, I can say output of IR optimization. So remember, IR optimization output is this. So this is output of IR optimization. Okay, so this will be the input to the code generation phase, to this code generation phase. And this code generation phase, it will give you the target assembly code. Okay, so like this. This is the target assembly code you are going to get. Is this clear? So very simple. This is the target assembly code you will get. This is the target assembly code. Remember one thing. Remember one thing. This is machine dependent. This is machine dependent. Actually, we cannot do anything here. Why? Because this is machine dependent. Means in your machine, this instruction is there. All these instructions are in the instruction set. Okay, this is machine dependent. And actually all these instructions, they are in the instruction set of the machine. They are in instruction set of the machine. They are in the instruction set of CPU of machine. Okay, so remember, this is your machine dependent. The result, this result is machine dependent because this is the target assembly code. And this target assembly code, that is, you already know, this is machine dependent. Okay. So, and the final stage, what is that? The last stage, that is code optimization, means machine dependent code optimization. Okay. This assembly code that you got, the machine dependent assembly code that you got. Now, can you optimize that? This is the point. We can optimize that also. Okay. So remember, this is the code you got, right? Yes or no? What is this? This is the code that you got. So notice one thing. We got this code. This is the output of code generation, right? This is the assembly code that we got. This is the assembly code. This is machine dependent. Okay. This is the assembly code that we got. Now, this is machine dependent. Now this you can optimize. Okay. You give this to the optimizer, machine dependent optimizer. To this optimizer, you give this input. Then this will give you optimized assembly code. Optimized assembly code. Optimized assembly code you will get. Okay, let me give you one example. Let's assume that in your machine, in your CPU, let's assume this instruction you have. See, here basically what you are doing, notice here, please notice here. These are the variables. Okay, these are the variables. These are the register. This is your register 4. This is your register number 4. These are the registers. Like this is R6. Okay, what is this? This is R6. This is the register R6. Okay. Actually, if you notice in this code, what is happening? Can anyone tell me? In this code, actually, in this code, what is happening? In this code, actually, this is happening that first you are adding R2, R3, and you are putting in what? R2, R3, you are putting in R1. Yes or no? This is the first thing you are doing. Then what you are doing? Tell me then what you are doing. Then you are putting in R4, you are putting R1 plus R4. Yes or no? This is what you are doing. You are adding these two, you are adding R1 plus R4, and you are putting the result in R4. Here you can notice you are adding R2, R3, and you are putting the result in R1. Okay. What is this? This is a set if less than. This means set if less than. What this means? This means set if less than. Is this clear? Set if less than. So what this means, set if less than? What this means if this R1 is less than R5, then what you do? If this R1 is less than R5, if R1 is less than R5, then what you do? Then you set this R6. Then you set this R6, means R6 becomes 1. Then R6 becomes 1. Is this clear? Please tell me. Let me know. Means this, see, SLT. What this SLT means? This SLT means set if less than. Set if less than means set this R6. Set this R6 if R1 is less than R5. If R1 is less than R5, then set this R6. Okay, is this clear? And finally, this is branch if equal. This is jump if R6. Okay, if R6 is set. So if R6 is 1, if R6 is 1, jump to loop. Okay, if R6 is 1, then jump to loop. So here, jump to loop if R6, jump to loop if R6 is 1. So this is your code. Now, you just tell me one thing. Let's assume, I'm telling you, let's assume there is an instruction in the machine, in your CPU. Let's assume there is an instruction. Okay, assume in CPU instruction set. Because now everything is machine dependent, remember. Now we are in the territory of machine dependent. Now everything is machine dependent. Okay, so let's assume that in the CPU instruction set, this instruction is there. Following instruction we have. Following instruction is present. Following instruction is present. Okay, see what I'm saying? I'm saying just assume that in the CPU instruction set, in the processor instruction set, let's assume the following instruction is present. What is that? The instruction is like this: branch if less than. Branch if less than. Okay. So here something like this, like for example, this type of thing, R S branch to some location L1. Okay, what this means, let me tell you what this means. This means branch if less than. Okay, this means jump if less than. Jump if R is less than S. Where to jump? Jump to L1. Yes or no? Jump to L1. Jump to L1 if R is less than S. So let's assume this instruction you have. Just assume this instruction is present in the CPU instruction set. Now can you optimize this? Now can we optimize this? Did you understand the question? Did you understand my question? I'm assuming in my CPU instruction set, in the CPU, this instruction is there. Okay, this instruction, branch if less than, means if R is less than S, then you jump to L1. Then you jump to L1. Now can we optimize? Now can we optimize the previous assembly code? Now can we optimize the previous assembly code? And the answer is yes. Now what you can do? Now the answer is yes. Basically, what you can do, you don't need these two instructions. Okay, let me tell you. Now something like this will happen, that now you don't need these two instructions. See what will happen. These two instructions you don't need. Yes or no? You can combine these two instructions, right? Notice, please notice. Can you combine them? These two instructions, can you combine them? Can you combine them? Let me know. Just look at these two instructions and tell me, can you combine them now? We can combine them, right? We can replace these two with what? We can say branch if less than, okay, branch if less than. If R1 is less than R5, then you branch to loop. Is this clear or not? Please tell me. These two instructions you can replace with one instruction. These two instructions you can replace with one instruction. What that means? Means these two instructions. Look at these. Okay, these two instructions. Now you can replace with one instruction. You can replace with one instruction. Branch if less than. Branch if less than. $1, $5, go to loop. So this is how you can do. Understood? Very good, Satyam. Excellent. Very good. So one instruction you can put. So finally, the answer will be, what will be the answer? So you can easily see these two instructions you can merge and this instruction you can get. So you got an optimized code. Yes or no? Did you notice? So this is your optimized assembly code. This is the final output. This is the optimized assembly code. And this is the last output of the compiler. This is the last output of compiler. I hope you understood all the phases. Please tell me, did you understand? Did you understand the machine dependent code optimization and machine independent code optimization? See, in the machine dependent code optimization, did you notice we are using the features of the CPU? Did you understand? Notice that in the machine dependent code optimization, here we are using the features of the CPU. Like this instruction is there in the CPU or not? In the instruction set of the CPU, do we have this instruction or not? Please tell me, did you understand? In this machine, this is machine dependent code optimization. In this machine dependent code optimization, we are using the features of the CPU. We are using the features of the processor. But in this IR optimization, we do not use features of the machine. Okay, is this clear? So this is a machine independent optimization and this is machine dependent optimization. And did you understand all these things? The complete sequence, did you understand? Please tell me. From lexical analysis to machine dependent code optimization. Everything, did you understand? Let me know. Let me know, did you understand everything? Please tell me. So that's it. Okay, this is the complete overview. This is a detailed overview of compiler phases, the phases of the compiler. With help of one example, I have told you what every phase will do. Okay, and I also told you what is intermediate representation, how to optimize the intermediate representation, how to generate the code, okay, the machine code, or I can say the assembly code, how to optimize the assembly code. So basically, we have seen the output of every phase. What the input of every phase, what is the output of every phase, what every phase will do, what is the task of every phase, what is front end, what is back end. Okay, so basically everything related to this is the complete detailed overview of compiler. Please tell me, did you understand? Let me know. Just let me know, did you understand the complete overview of compiler?